Hello, math fans. I'm Dr. Andy Lovelace, longtime instructor at the University of Washington. I'm going to be teaching Calculus 3 over the next several months. As I do it, I was going to make little supplemental videos. I'm going to try to keep them short. I know some of my videos get longer. Let me know if this format is interesting to you. What I'm going to do is pull ideas that are appearing in some of our homework and take them maybe a little further than I would in lecture, but just do little snapshots with visuals. I've really been enjoying making these 3D visuals. And so I'm just going to try to cover topics in little snippets. And so that if a student in class is struggling, this is something else they can look at and play around with. Students in my class, I'm also going to be sharing these graphs with you. In the beginning of this course, we're playing around with working in 3D. So the first thing, maybe I'll show the first one and then I'll break off and do other ones, but is distances. And part of what we're learning, historically, I didn't like showing these visuals because I was like, part of what we're learning is how to visualize. So I feel like I'm giving too much with the visuals, but the visuals seem to be exciting for people. And so if it gets people engaged, to me, it's worth it. It's a good trade-off. We start with this idea of distance. So maybe I'll just start with a little explanation. Where is that coming from? It's coming from this. So let's just do distance. I'll leave the visual for another part. So let's say we have 2 points. And for now, let's assume one of the points is at the origin, which we're going to call 0, 0, 0. In my class, we would talk about these things, how this is a right-hand coordinate system, and I'll play around with it. We'll do several things in the class. But let's say you move along the x-axis for a while, and let's call that the change in x. I'm trying to keep things as simple as I can in this explanation, but it's really the difference between the x-coordinate. Then let's say you walk along the ground, and let's call that the change in y. So I'm doing this without any 3D visuals. The 3D visuals you have to wait for the next video. One could then ask the question, which is how long is the edge of this triangle, this hypotenuse of this triangle along the ground? And that's the regular old 2D distance formula. Let's call this d for a minute. And what you get is that this squared, it's a short little proof, but since this is such a valuable tool, the fact that we can do distances, it's this. So you get that's that length there. That's the normal 2D distance formula. You might ask yourself if you've seen that before. X2 minus x1 squared, y2 minus y1 squared. That's that formula. Change in x squared, change in y squared, normal 2D distance. So y, yeah, we might be able to say that looks like the 2D distance formula, but why does it work out that way? It's a great question to be asking. Well, here's what you do. Let's assume you also go up. What do I mean by going up? Let's assume someone gives me a change in z as well. But instead of going up like that, you just go straight up from this point right here. And I've done sort of a poor job of drawing it because it's going to go right over the top of my d. So I'm going to erase this. Let's erase this. In fact, let's fix my drawing a little bit. I know I just erased a few things, but I'm not worried. I mess up all the time. Maybe I shouldn't admit that, for I want people to take my class. Okay, so here we have this little dotted distance, d. We're going to go straight up, and here we go. There we go. Sound effects are free. This is all free. And here I'll draw a little this dotted line so you can see it up above. Okay, our goal when we're trying to find the distance between 2 points, in this case the origin, right here at 0, 0, 0, and this point up here, what are we actually doing? We're trying to find this distance. And that's about the best 3D drawing you're ever going to get from me. What is that distance? This is the clever observation, if you've never seen this, is there's another right triangle here. And what can I say about that right triangle? And I never go through this proof in as much detail because no one cares in the class. They just want me to tell them the formula so they can go start using it. So this is part of what we're doing here. This is the d. And then the real distance I want is this. And so the observation is the thing I want, the question mark squared, equals d squared plus this squared. And it's really kind of beautiful. So the thing I want, let's call it something besides question mark. I guess I'll call it C. I feel like that's not very original. C squared. What can I say about C squared? Aha, it's kind of a beautiful little proof. It's a little extension. So C squared is the change in X squared plus the change in Y squared plus the change in Z squared, and I can take the square root, and that's this distance. So that distance works in 3D. The moment you have distance, you can do a bunch of things. You can figure out if 3 points form an equilateral triangle. How can you do that? You find all 3 distances. Are they the same? Do they form an isosceles triangle? We have homework questions like that in tutorials, like how am I going to figure this out? Compute the 3 distances and see if they work to do what you want. Okay, so I'll leave it at that. That's just kind of an introduction to our first tool. All right, and then I'll make several short videos on some other little observations. Hope this is interesting to you. Let me know if this sort of format is helpful.